So welcome to the last day of the first course. As you must have noticed, when you're sort of climbing a mountain, you watch your feet and walk one step at a time. But at the end of the week, you're on a peak. I would sort of look at Dipankar's lectures as something like that. So you think that you have just walked a little, but what you have sort of been exposed to is a kind of height which you will really need to follow up when you go back and look at the references which he has given you. So without further ado, Dipankar.
Thank you, and good morning and welcome to this last lecture. So we will devote today's lecture almost entirely to binary systems. So we found yesterday, both in the lecture and later on in the tutorial, we saw various aspects of the evolution of binary systems. In particular, we saw that if you have a binary system where mass exchange takes place, the orbital period can change significantly. So if a more massive star transfers matter to a less massive star, the orbit shrinks, and then when the situation reverses, the orbit expands. What does happen though, if you look at a typical high mass binary, so say you have the mass of the donor star. So you start with some mass m0 over here, and what I'm going to plot here is the R, but two different radii. One is the Roshlov radius, and the other is the stellar radius. So R and RL. So Roshlov radius, as you know, is going to follow the separation. The separation becomes smaller, Roshlov radius will become smaller. If the separation becomes larger, Roshlov radius will become larger. So as we saw yesterday, it will do something like that. It will initially decrease. So this is the way the evolution is going. The stellar mass starts at m0 and then starts decreasing because mass is going to the other object. What happens to the stellar radius? The point at which mass transfer starts occurring, stellar radius has just reached the Roshlov radius. That's when mass transfer starts occurring. Now, if now look at the equilibrium radius of the star, given the disturbance that is being caused by mass transfer and the evolutionary sequence. Remember, the radius was smaller earlier and it was beginning to expand. So just because some matter has been taken away, that expansion is not going to stop. So it is still going to expand. So you are going to have radius slowly increase, and then when significant matter has gone down, gone away, radius is going to begin to decrease. Eventually, the time will come when it is going to drop precipitously. It so happens that this point is not reached until the entire envelope of the star is lost. It begins to drop, stellar radius begins to drop dramatically because now the envelope is completely emptied and you're left with the more massive, more dense part of the core, which was doing nuclear burning to start with. So eventually what you're left with here is just the core mass. Until the point the stellar radius goes below the Roshlov radius, mass transfer was still occurring. When the star shrinks below the Roshlov, mass transfer will stop. So you start with a big star and you're left with the core of the star. So this is a very efficient way of removing the entire envelope and exposing the nuclear burning core. So this core, of course, now has a much smaller mass than you started with, and what you started with. So you started with, let us say, 2 stars. Let's go to the example of 20 solar mass star and 8 solar mass star. So there was a Roche lobe around both these. 20 solar mass star fills the Roche lobe, starts transferring matter onto the 8 solar mass star, and the separation decreases, and that makes the Roche lobe smaller. And then at some point, the mass ratio reverses. So once the mass ratio reverses, the relative size of the Roche lobe of the donor star becomes even smaller than it started with. So, and that's what gives you this evolution. So at the end, you are now left with so this will be about maybe 2.5 solar mass, and let's call it 4 solar mass, and you now have a 24 solar mass star, and this has happened very quickly. 8 solar mass star was undergoing its own pace of nuclear evolution. It was very far away from exhausting the hydrogen in the core. Now we have rapidly dumped some hydrogen on top of it, hydrogen and helium. So the central pressure will increase, central temperature will increase, and a larger nuclear burning core is going to form because of this. But it is not going to happen, it's not going to make a great deal of difference in the evolutionary state of the star immediately. So the star is not going to leave the main sequence. It is still going to be largely hydrogen burning interior. So it stays well within the Roche lobe, and it takes a much longer time to evolve. But one thing that has happened here is assume there was no mass transfer. And at the end of the evolution, the 20 solar mass star produces a neutron star, and the rest of the mass is lost from the system. So how much mass would have been lost from the system? Consider 1.5 solar mass being locked up in the neutron star. So you would have lost 18.5 solar mass. That is much larger than half the total mass of the system. So if such a thing happened, then the orbit will become unbound. So you saw yesterday that if more than half the mass is ejected from the system, the orbit will become unbound, and you will get just these 2 stars going in their own way. It will no longer remain a binary. Now, after this point, when this 4 solar mass star, then 4 solar mass helium star, now leaves a 1.5 solar mass neutron star, you are only going to lose 2.5 solar mass. So orbit will become eccentric, but it will very much remain bound. So the binary remains intact as a result of this first stage of mass transfer. Now, at the end, I'm going to get the evolution is not finished. The other star is to evolve yet. So given enough time, this star is now going to undergo nuclear evolution and start expanding, fill its Roche lobe. Then what's going to happen? So once this fills its Roche lobe, then mass is going to go from here to the neutron star, right? This neutron star is now going to start accreting matter. The accretion onto a neutron star has several consequences. First, the amount of matter that the neutron star can accept falling on it is limited. We have discussed that yesterday. There is an Eddington accretion limit. It's up to the point that the neutron star can accept matter. The typical mass transfer rate for a Roche-Loeb filling 24 solar mass star is going to be much higher than that. So neutron star will only accept about 10 to the power minus 8 solar masses per year. What is going to happen to the rest of the matter? This evolution, of course, it begins to transfer matter even before the star has actually filled the Roche-Loeb, because the star has an extended atmosphere. Even before the photosphere has expanded and filled the Roche-Loeb, the atmosphere would have exceeded the Roche-Loeb and would have been accreted. At that point of time, the accretion rates are a little lower, and accretion is steady. You will see that matter being accepted by the neutron star. Matter falling on the neutron star is going to get heated because of the gravitational energy that's being released. They get heated to tens of millions of degrees temperature, so you get X-rays from them. So a situation like this, where you have the Roche-Loeb just outside, it's called beginning atmospheric Roche-Loeb overflow. Or even before that, just the stellar wind itself being captured by the neutron star. This, or wind accretion, will provide a steady source of mass falling onto the neutron star, and then this is going to generate X-rays, and such objects will be called high mass X-ray binaries. High mass because the mass donor star has a mass larger than the neutron star mass. So that's the distinction. When you say low mass X-ray binary, the mass donor star is less massive than the compact star. High mass X-ray binary, mass donor star is more massive than the compact star. Material arrives at the surface of the neutron star. But what is the trajectory? Mass leaves this system. But remember, this is in an orbit. Mass does not leave in a manner that it can directly radially shoot to the neutron star, because it's got angular momentum. Even if it leaves the star, if I look at the orbit from above, donor star, let's say the orbit is anticlockwise, then this matter that is leaving will also tend to orbit the neutron star. It's a little stream of matter which will orbit, come back and intersect and collide with itself. And such a collision is going to lead to some loss of energy and some exchange of angular momentum. Therefore, next time this stream goes towards the neutron, goes round, it is going to follow a inner trajectory. This now has less total energy, less total angular momentum. This is going to continue. So you're going to get this matter spiraling in onto the neutron star. And now imagine that this is a stream that is being continuously supplied by the donor star. So this thing is actually going to be filled. And such a structure is what we call accretion disk. And the accretion disk, of course, because of this friction, collisions, etc., the accretion disk is a hot object, and the temperature keeps increasing as the accretion disk reaches the center. So outer parts are a little cooler, inner parts are hotter. So higher energy X-rays are emitted from inner part of the accretion disk. And as you go out, you will go to softer X-rays, and at the outer edge, you might get ultraviolet optical kind of emission. This has been studied in great detail for ages, and we know a fair amount of about the properties of accretion disk, not just in a neutron star binary, but binaries of all kinds. But let's focus on the very inner edge of the accretion disk, and then see how does the matter finally arrive on the surface of the neutron star. We have said yesterday the neutron stars are characterized by strong magnetic field and fast rotation, right? So if I now zoom in on the inner part, so now you have a neutron star, and let's say it has a dipole magnetic field. Imagine accretion disk is trying to cross this magnetic field. When the field is weak, it's no problem. But as the matter comes closer and closer to the neutron star, the strength of the magnetic field becomes larger and larger. Because it's at the zeroth approximation, if you consider this to be a dipole magnetic field, the magnetic axis, then the field strength will drop off as 1 over r cubed. So as r becomes smaller, the field strength begins to rise considerably. So there will come a point where the kinetic pressure of the incoming flow and the magnetic pressure due to the magnetic field will sort of become comparable to each other. And when that happens, then the magnetic field is going to arrest the incoming flow. So if the flow is coming in a disk, then let's say this is the point at which the disk gets arrested. Further in, the magnetic field is too strong. It's pushing back, so the disk is not able to go in any further. So at this point, matter will entrain the magnetic field, and then it will flow like this. The matter will now take such a trajectory from both sides. So instead of coming and covering the neutron star uniformly, matter will make its way to the magnetic poles. So these magnetic polar regions now are going to receive these incoming matter streams, continuously releasing gravitational energy, and as it falls on the surface, it makes the surface very hot. But these are small regions of the surface which are hot. Now assume that the neutron star also has a rotation around some other axis. So if you happen to be somewhere down there, this hot spot will come in and out of your field of view once every rotation period. And therefore, the X-ray emission that you see from the neutron star is going to undergo a periodic modulation at the spin period of the neutron star. And we call them accreting X-ray pulsars. Unlike radio pulsars, which are not accreting, and emission is due to magnetospheric processes, and you have non-thermal radiation beams which are attached to the magnetic field lines, which causes the pulsar appearance of the pulsar. Here, it's a thermal emission from the surface, from confined hotspots, and they'll come in and out of your field of view, and it will give you the observed modulation in X-ray intensity. There are subtle things that you have to take into account when you try to imagine how this modulation is going to look like as a function of time. If you have the hot spot, consider one hot spot on the surface of a neutron star, and consider an observer over here. Radiation from here does not come directly following a straight line. This is a thermal hotspot on the surface. So from this little point on the surface, radiation goes in all directions. Excluding the inward direction, radiation escapes in all directions. So this is an isotropic emitter emitting in all directions. The radiation at this point that will reach the observer would have left the surface at an angle which is not directly pointing to the observer. Typical trajectory will be like that. Can you tell me why? Light bending in strong gravity. So the strong gravity of the neutron star will bend the trajectory of light. And that bending is therefore going to decide which ray of light actually reaches you. In general, this will not be just a point, but there is a region. So you're going to have to integrate over all the trajectories coming from all parts of this region. Now, what's the difference? If I take a light ray which is moving this way and coming there. And instead, if I had taken a light ray which is joining straight from this point to that point, how would it be different? I mean, does it have any material consequence? Yeah, except these are objects which are not able to resolve by any imaging process. They're very tiny. What about the total flux? If you take something on a surface, this is the perpendicular to the surface. You observe it from an angle theta. How much flux is going to go in your direction? Very good, cos theta, right? Instead, if light goes like this to you, which eventually becomes theta, but it starts at theta prime, how much flux are you going to get? Cos of theta prime, right? So you are actually going to receive more flux, although you are looking at it at a larger angle. So the entire flux versus angle relationship is going to change. So if you now take the full hotspot distribution and try to model how the intensity is going to behave as a function of time as the star rotates, that will be strongly influenced by this light bending. And what is the light bending dependent on? Correct? So what properties of the neutron star? I mean, it's the mass, right? It's only the mass. And radius, because it depends on the gravity at the point where the radiation is leaving the surface. So it actually depends on this quantity m by r, which is called compactness. So if you actually now compare observed pattern of radiation from the hotspot with what is intrinsically emitted, you have a signature of the compactness that you can discern from this observation. So you can derive this quantity. There are additional quantities that you can also derive from hotspot observations. So we have this hotspot, it is spinning, right? It's spinning about an axis which does not pass through the hotspot. So at any point of time, the hotspot is either approaching you or receding from you, right? So when it's approaching you, the radiation is going to be Doppler shifted to blueward side when it comes. When it's going away, the radiation is going to be Doppler shifted to the redward side. So if you look at the continuum X-ray spectrum, and then look at the color of the spectrum, that means you take hardness ratio or take the spectral slope, then you'll be able to figure out also this how much Doppler shift is present. How much Doppler shift is present now depends just on the apparent motion of the hotspot, right? You know the spin frequency, therefore it just depends on R, right? So color variations will give you R. But not exactly R, because there is also a gravitational redshift that you have to take into account. And when you look at the net expression, it will have R, and it will also have a function which is related to the gravitational redshift, and that gravitational redshift is again related to the compactness. It's a function of R and compactness. So you now measure the intensity pattern and measure the color pattern. From these two measurements, if they're accurate enough, you should be able to find the mass and radius of the neutron star. Okay? And this nicer mission is designed to do exactly that. They even take cleaner systems where currently there is no accretion. So you can have some fast spinning millisecond pulsar which produces X-ray emission, where the X-ray emission is not contaminated by emission coming from accretion disk or anything like that. And then look at these aspects. Look at the intensity variation of the hotspot and the color variation. And using that, the mission is trying to constrain mass and radius of neutron stars. This is a long-term project, and some significant progress has been made, but there is more to be done. That's definitely one of the important EOS constraints that one is hoping to derive relatively near future.
Sir, I have a question.
Yeah.
So it's related to the accretion. So why does accretion start with a disk shape in the first place? Why doesn't it start with like a spherical geometry?
Yeah, that's because we are starting with some angular momentum, right? So if you had very low angular momentum, then you will have a more spherical type of accretion. For example, if you do the wind accretion phase, where what you're accreting is this stellar wind escaping the star, and then because of the gravity of the neutron star, those trajectories will get bent, some of that matter will fall onto the neutron star. That will be more spherical, although very close to the neutron star, you may still get an accretion disk, but the specific angular momentum in such a flow is much less. So you will get a more spherical type flow in those cases. But if you have actually Roche-Lobe overflow, the angular momentum content is very high. Specific angular momentum is equal to the specific angular momentum in a Keplerian orbit. Therefore, it will tend to follow the Keplerian orbit. We will not have time to cover many of the rich details of this and phenomenology of this kind of emission. But you can read up some of the references that I've given for binaries. And if you can get hold of this new book, which also I have referred, that's an excellent book, covers almost every aspect of neutron stars in binary system. Okay. So at some point, the evolution of this star is going to be over. What do we expect then? I think you have to go through one more step before that. This is fine, in this kind of accretion scenario is fine, as long as we are in beginning atmospheric Roche-Lobe overflow or wind accretion, where the accretion rate is small. When this massive star actually fills its Roche-Lobe, the mass transfer rate will be very high, which will much exceed the Eddington rate of the neutron star. So once that happens, Now you see that the neutron star is here and the donor star is there. Is the Roche lobe, which is actually much smaller around the neutron star. Draw it, move to scale. Neutron star is over here. And you have L1, L2, L3, and so on. So you transfer a lot of matter, which is coming to fall on the neutron star. Neutron star is generating radiation. The radiation is so high that it pushes back on the matter. Only a small fraction of the matter can get accreted onto the neutron star. The rest of it is being pushed back by radiation, and therefore it will have to expand back. It's going to expand back and fill these regions. So if you fill this, then you can see that matter is actually going to leave the system, because you reach L2 and L3, and then matter just leaves the system. Not only that, the envelope of the star, because of this flow back, has now become something where the neutron star is actually sitting inside the expanded envelope of this donor star. The orbit is still continuing, but the neutron star in this orbit is moving at a different speed compared to the envelope, because the envelope is attached to the other star. So there is a friction in this orbit. A situation like this is called a common envelope phase. In a common envelope phase, now the neutron star's orbit, so neutron star is basically going around inside the other star, and it's in the process, the friction is generating a lot of energy. Orbit is shrinking rapidly because orbital energy is being dissipated. And all this energy that is being dumped into the envelope is eventually going to expel the envelope. The envelope has a binding energy on the donor star. When the amount of energy that has been dumped by this process exceeds the binding energy of the envelope is actually going to get expelled. But in the process, the orbit will have shrunk a lot, because it's at the expense of the orbital energy that the envelope goes away. There can be situations where the neutron star can end up at the center of the other star, in which case the two stars would have merged. And there are such kind of objects go by the name Horn-Zitkov objects. Where neutron star merges with donor. Else, you will have a very compact binary, neutron star, and the donor core, which could be in the verge of going supernova. Now, neutron star only has 1.5 solar mass. The donor core, depending on the mass that you started with, could have a few solar mass. This also now will go supernova. And once a supernova happens, some matter is going to be expelled. If that matter now is more than half the total mass of the system that you now started with, then it can lead to disruption of the system. So you will get 2 neutron stars going their own way. Or you can get 2 neutron stars bound in an eccentric orbit. And it's the latter which then gives rise to systems like Hallstatter binary pulsar, very compact, eccentric, 2 neutron stars in the system. And they are also the prototypical objects which LIGO was originally built for. There are some additional complications which I am not going to go into the detail now. And one is that the supernova explosions, we are assuming that they are spherically symmetric with respect to the progenitor star. Often they are not. So there is a little bit of asymmetry in the mass ejection in the supernova. So that results in a kick to the central object that remains because of the momentum conservation. Right? So if the mass that is ejected has a net momentum in a certain direction, the compact object will get a opposite net linear momentum. Large part of the mass is ejected, so therefore the asymmetry in the mass ejection could be quite small, but the resulting kick could be quite large. So neutron stars, when they're born, we see that they could receive kicks of the order of a few hundred kilometers per second, going up to thousands of kilometers per second sometimes. So that can have an additional effect. For example, even if less than half the solar mass has been ejected from the system, if it has been ejected asymmetrically because of this extra kick, the orbit can get unbound. But more interestingly, even the reverse can happen. Even if more than half the system mass has been ejected, if the kick is suitably directed, it can keep the system bound. Although in a spherical explosion, it would have become disrupted. So all these different combinations are possible. So at the end, at least in some fraction of the cases, you will produce a eccentric double neutron star binary, or you will just have 2 neutron stars unbound, moving by itself.
Is there a possibility that the matter which is ejected in the supernova explosion of the donor core gets accreted onto the second neutron star?
I think here you need to do a calculation, right? The matter is moving at 10,000 kilometers per second, right? So you can ask what fraction of that matter will be intercepted by the gravitational influence of the neutron star. And you'll find that it's a very, very tiny amount, right? Because the speed of ejection is so large, the amount of matter from this which can get bent, get attracted by neutron star's gravity and fall on it, is a very tiny fraction. So yes, some fraction will get accreted, but it will probably be a very small fraction of the solar mass. Yeah. It can if it accretes enough matter. So suppose you have started with 1.4 solar mass neutron star, right? And let's say the neutron star mass limit is 2.5 solar mass, let's call it. How much mass does it need to accrete? 1.1 solar mass. At what rate can it accrete? So it has to accrete for at least 100 million years at the same rate for it to reach that mass. These massive stars have entire main sequence lifetime is only over a few million years. The mass transfer lifetime is only in thousands of years. So these systems are not capable of dumping enough mass on the neutron star for it to go over. But the kind of system which I'm about to discuss has the potential, but still not truly enough. So this is one class of binaries. The other class of binaries is where you have a neutron star in a binary with a low mass star. The binary companion has a mass which is about a solar mass or less. How can such a binary form in the first place? Because if you started with, let's say, neutron star progenitor, it's even start with 10 solar mass and 1 solar mass star. If the first mass transfer was conservative, that 1 solar mass star would have gotten converted already to several solar mass star, which is more massive than the remaining neutron star. So how can such a binary form? We see in a lot of them. Neutron star in binary with a low mass star, which is 1 solar mass or less. Two things can allow such a thing to happen. So let's call this now low mass extreme binaries. One possibility is that you start with really extreme mass ratio binary, maybe 20 solar mass and 0.8 solar mass, something like that. In that case, there's a huge difference in the Eddington accretion rate of the two masses themselves. So when the first star evolves and evolves in a very short time scale because its mass is large, then the Roche-Lobe overflow, which is going to supply matter onto this other star, dumps matter at such a high rate that most of it actually goes out of the system. The low mass star now does what this neutron star did over here, that is enter a common envelope, and at the expense of orbital energy, you expel the envelope of the other star. So low mass star would have accreted a very small amount of mass in this process, maybe 0.1 solar mass or something. So that's then the final configuration. You have a neutron star in binary with a low mass star. There is yet another possibility, which is also very interesting and very rich. And that's what happens in stellar clusters, like globular clusters. Globular clusters are tight collection of stars. There could be 1 million stars to tens of millions of stars, tightly gravitationally bound. And these are independent cluster entities which are orbiting in the potential of the host galaxies. For example, Milky Way has hundreds of such globular clusters. Because the stellar density is high, the stars in a globular cluster system can have frequent gravitational interactions. And these frequent gravitational interactions can cause several interesting effects. So let's consider one compact star, which is of our interest, which has formed, and it passes by a regular star. I have to also mention at this point that globular clusters do not see multiple phases of star formation. Whatever star formation has happened early, and since then no new stars have formed, and since all the massive stars have already completed their evolution, the stars that you see today are all of low mass. All the more massive stars have left compact star products, which are also present in the globular cluster. Let's take one such compact star. Let's take a neutron star passing by a star which may be a 1 solar mass star. As the neutron star passes by, it is going to raise tides. Cause tidal deformation. As the neutron star passes by, the tidal deformation is going to undergo some dissipation within the star. The dissipation is going to cause this bulge to lag the direction of motion of the perturbing star. And so then there will be a talk, exactly as we were discussing yesterday about Earth-Moon system. So this is going to transfer angular momentum from this trajectory into the interior of the star. So it's going to aid the spin up of the star, and B is going to pump energy into these tidal bulges, which can then dissipate due to internal viscosity. That means the total energy of the orbit decreases. If it decreases sufficiently that the net energy after this encounter is negative, then after this, the neutron star is going to get bound into an orbit. This is called tidal capture. Happens in two-body interactions in globular clusters, and there is a significant number of these that happen. So now you have a free neutron star and a free low mass star. They undergo tidal capture and form a binary, which will be very much like the binary that will lead to a low mass extra binary. And globular clusters are indeed very rich in low mass extra binaries. We know that this stellar encounter processes can take place and can produce this. But tidal capture is only one such process. You can also have these normal stars in binary systems. You have two normal stars in a binary system. And let's say a neutron star is passing by. this is, in this trajectory, this comes close to one of these objects, which is closer than the average distance between the neutron star and the other star. So this is the only dominant entity at that point of time. After this thing forms, this is again going to scatter off other stars, and then more processes are going to occur. So this is one such process. You have a binary, and a compact star or a third star comes nearby. Yeah. No, so all you need is the amount of energy dissipated in the tide to be more than the to be enough, so the total energy becomes negative. That's all, right? So you had some amount of kinetic energy in the orbit, which was positive, and there was already a gravitational interaction, which was negative. So there was if you add these two up, you have a total energy. If those two are not bound, this total energy was positive above zero. As long as you dissipate enough energy to bring that below zero, it will become a bound orbit. And it has to happen in that interaction. Otherwise, the neutron star will go away and then interact with something else, right? So you have to have dissipated enough energy in one interaction for it to get captured. And if you put in numbers, you'll find that this is quite ubiquitous. It happens quite often in a globular cluster. So this other process that I was talking about is, so now, because of a similar process, but now interacting with the orbit, the neutron star can exchange energy, kinetic energy, with the orbit. As a result, you can form a temporary three-body system, bound three-body system with the compact star and then two other low-mass stars. Three-body systems in general are unstable. Usually, in such a system, after a few chaotic orbits, the lightest mass is ejected. And the two relatively heavier masses remain bound in a binary system. Now, since most of the stars today, regular stars we are talking about today are low mass stars, a neutron star typically will have a heavier object. All this that I'm saying goes also for black holes, by the way, which stellar mass black holes which are formed in globular clusters. So eventually you're likely to form a binary with a neutron star and a low mass star. And the relatively lower mass object of this other binary is going to get ejected. So this is a exchange process in a binary system. Not only this, you can have binary interaction and companions can be exchanged. So over the course of the lifetime of a binary in a globular cluster, many such interactions can happen. And then different partners can get swapped and so on. And as you can see, in every case where components of different masses are involved, the probability is higher for the more massive of the components to remain in binaries. There's another effect that happens for all such encounters, is that you have a binary system, you capture a neutron star, and then you form a new binary system. This new binary system is going to form with a certain amount of the center of mass motion. It is not going to be at rest with respect to the initial binary system. The initial binary system had a speed typical to the stellar speeds in the globular cluster. This will have an overall, over and above that, a kick. because of this gravitational interactions. And the more tight the binary is, the bigger is going to be the kick. And eventually, the kick may be large enough for this binary to get ejected from the globular cluster altogether. And these binaries will then be floating around in space. They can be found elsewhere in the galaxy. And you would not know that the system was actually formed in a globular cluster, but it is now found in the galaxy because it's been expelled. So in the 1990s, when this was all being worked out, there was a lot of activity, Stirl-Finney came up with a statement which very succinctly summarizes this process. His statement was that through promiscuous swapping of partners, binaries in globular clusters get progressively degenerate and then are expelled for their sins. Okay, so that very succinctly summarizes the processes. You can have multiple stages of these interactions. And if you look at large black hole binaries, like the ones that we're seeing in LIGO, the more probable formation processes are through these exchanges. So mostly likely to have come from globular clusters where black holes initially form, and then through multiple swapping of partners, two heavy black holes end up in the same binary. Because at every stage, the average mass in a binary, remaining in a binary system, increases. So you are then, through any of these processes, you end up with a low mass X-ray binary system where you have a neutron star and you have a low mass star. Let's say one solar mass star. And let's say this one solar mass star has expanded and filled its Roche lobe. Now it transfers matter to the neutron star. What's going to happen to the orbit? We have discussed this multiple times. This is 1.4 solar mass. This is 1 solar mass. What's going to happen to the orbit? It's going to expand, right? If it's going to expand, then suppose I take this 1 solar mass to start with on the main sequence. Suppose there is a contact in the main sequence. I take away some mass. The mass of this star reduces. In main sequence, the radius of the star is proportional to its mass. So the radius of the star is going to become smaller. What's going to happen to the Roche lobe size? Going to become larger. So is the mass transfer going to continue? It will stop. We just transfer a little matter, then the star shrinks and the Roche lobe expands. Obviously, there is no contact. So how can mass transfer be sustained in such systems? At least in the cases where the mass-radius relation is of a positive slope. That's where something that we discussed yesterday in the tutorial becomes extremely important, and that is angular momentum loss. So this is sustenance of mass transfer. So angular momentum loss, you can have magnetic braking. These are solar type stars. It's like the sun is experiencing magnetic braking all the time. These stars can also experience magnetic braking, and through tidal interaction with the neutron star can drain the orbital angular momentum and orbital energy. So that is then going to drive the separation to become closer and closer with time. And gravitational waves. As we saw yesterday, when the separation becomes really small, then the gravitational waves become the dominant mechanism. When the separation is a little larger, then the magnetic braking is the dominant mechanism. So typically that separation occurs at around 12 hours of orbital period. So if the orbital period is more than 12 hours, then magnetic braking is typically the this mass transfer driver, and if it's less than 12 hours, gravitational radiation becomes the main mass transfer driver. So now let us imagine what happens. You have this star which transferred a little matter, orbit expanded. It doesn't transfer matter anymore. Angular momentum loss is going to now bring the orbit closer together. Now it has to bring the orbit even closer so that the smaller star now fills its Roche. So orbital separation decreases with respect to the previous size, so that it now fills the Roche lobe again and transfers a little matter. And this repeats. But of course, it doesn't repeat in a stepwise fashion like this. It's a continuous, regulated fashion in which the orbit would decrease exactly at the rate, keeping in step with the reduction of mass of the companion star and consequent reduction in its size. If the reduction rate is due to angular momentum loss is larger, then the mass transfer rate will be larger. The reduction rate is a little smaller, orbital reduction rate is a little smaller, the mass transfer will be smaller. So the mass transfer rate will keep pace with the star continuously kept in Roche lobe contact while angular momentum loss is taking away the angular momentum from the system and making it shrink. So eventually, such a system will be left with a neutron star and a white dwarf when this finishes its evolution, a very small low mass white dwarf. And very short orbit of tens of minutes. So this is when this is for periods, initial periods, less than about, say, 2 days. Orbit shrinks. But if we look at periods, initial periods greater than 2 days, the main sequence phase of the low mass star will not fill the Roche lobe. The Roche lobe will be filled only when the star is now has completed nuclear burning at the center, and then it's now expanding due to nuclear evolution, and then it fills the Roche lobe. Transverse matter, the orbit expands, but now the star is in an expanding phase. The star expands and fills the expanded Roche lobe. Transverse more matter, orbit expands further, star expands and catches up with the expanding Roche lobe. So there the orbit is going to expand. And you'll be left with a neutron star with again a low mass white dwarf with hundreds of days orbital period. Here the orbital period is of hours. Remnants of both kinds are seen. And in both cases, as you can see, it's a really slow process. In case of this short period binaries, the time scale is just decided by the angular momentum loss and gravitational waves. This whole mass transfer process can last ten to the power of 9 years or so, billion years. This process is driven by the nuclear evolution of a low mass star. And this is also a slow process because the star is of low mass. And this can last for 10 to the power of 8 years. Now, we'll come back to this question that one of you asked. The neutron star can accept matter at the rate of 10 to the power of minus 8 solar masses per year. If you have a system which is transferring matter at Eddington rate on the neutron star for more than 10 to the power of 8 years, what can happen? So the neutron star can end up accreting a great deal of matter. And in some of these systems, it is possible that you can convert the neutron star to a black hole. Or at least you will end up with systems where the neutron star is in a binary, with a low mass white dwarf, but the neutron star itself has a much heavier than usual mass. Where do we find such systems? Where do we find such neutron stars? Let us come back and look at what this process can do to a neutron star. We have just described the radiation from a hotspot, but there is a lot more to it that the neutron star experiences in this process. Okay, let us say this is a distance RA at which the disk is arrested. So we call that the Alfvén radius. It is not too difficult to estimate how far that is going to be. Let's take the flow rate of the incoming matter. For the sake of argument, let's consider just a spherical inflow rate. So if m dot is the inflow rate, then I can write m dot as the area 4 pi r squared times rho is the density of this material at distance r times the inflow velocity. Inflow velocity at any distance r, let's call it the free fall velocity at r. And free fall velocity at any distance r is nothing but square root of 2g mass of the neutron star divided by r. This m dot is a constant quantity, so I can therefore write rho of r is m dot by 4 pi r squared VFF of r. So that is the rate at which This is the rate at which mass is crossing any surface. And at a distance r from the neutron star, the density, local density of the accreting material is this, accreting gas is this. So as this is coming in, it produces a kinetic pressure. And that kinetic pressure is nothing but rho v squared. Which is then m dot VFF r by 4 pi r squared. The flow will be arrested if the pushback from the magnetic field equals this. Magnetic pressure is v squared over 8 pi. We have to find the magnetic pressure at that particular distance. So that I can write as the surface magnetic field, B naught squared, times r star, that is stellar surface, stellar radius to the power 6, divided by 8 pi r to the power of 6, because B is proportional to 1 by r cubed. So this, then I will equate to m dot VFF r over 4 pi r squared, which is equal to m dot times square root of 2gm divided by 4 pi r squared and square root of r, so that is r to the power of 5 r's. So now I can take this and just evaluate the value of r. So I take this r over there, so I have r to the power of 7 by 2, 4 pi, 8 pi, so 2 is 1 by 2, v naught squared, r star to the power of 6, there is root 2 here, so let's make 2 root 2. Gm to the half. M dot. So as you can see that this will give you Ra will be proportional to V naught to the power of 4 by 7, m dot to the power of minus 2 by 7, and then you will have Gm and R star and so on. Let me keep these two terms for now. So if the neutron star magnetic field is stronger, then obviously the flow will get arrested at a larger distance. For a given magnetic field, if the accretion rate is higher, then the Alfvén radius will be closer. Fine. So what does this tell us? Let us now look at the Keplerian rotation speed of material at Ra. So what is omega k at Ra? This is square root of Gm over Ra cubed. So this will then be proportional to this is B naught to the power of minus 6 over 7. We get 6 by 7, m dot to the power of 3 over 7. Right? So the stronger the magnetic field, the smaller is omega k. And the higher is the accretion rate, the higher is omega k. Now, the neutron star is spinning already at some omega. So if I now compare the existing omega of the neutron star with this omega k, what is the neutron star in the magnetic field doing? At this point, it is entraining the matter and then making it spin at the same rate as the neutron star. Magnetic field is attached to the neutron star, matter gets attached to the magnetic field. So the matter is being made to rotate at the same speed as the neutron star. Now, if that speed happens to be the same as omega k, everything is hunky-dory. If that speed, if omega neutron star is larger than omega k at Ra, then this is going to get flung around at a speed which is larger than the centripetal force required to hold the matter in orbit. So it's going to exceed the gravitational attraction. Centrifugal force is going to exceed the gravitational attraction. So matter is going to get flung out. So matter lost, matter expelled. No accretion is going to happen. Rather, very little accretion is going to happen. If omega neutron star is less than omega k of Ra, then obviously the matter is being made to move slower and it is not, gravity is stronger, so it is going to follow the magnetic field and going to fall on the surface of the neutron star. So accretion takes place. But another thing happens. At the time the disk arrived here, the material had a certain amount of specific angular momentum. And that specific angular momentum is now larger than the specific angular momentum of the neutron star. Right? Angular momentum per unit mass is given simply by the omega times distance. So at that distance, you now have an angular speed of the disk, which is faster than the angular speed at which the neutron star is rotating. Now you're trying to couple it. So this matter is actually going to put a torque on the neutron star and try to spin it up. So here, matter will be expelled and similar torque will try to spin down the neutron star. And here, we're going to spin up. When omega k is Ra is equal to omega neutron star, then you have an equilibrium. So at if the accretion continues for a long time, then the system will evolve towards this equilibrium. So given an accretion rate and a magnetic field, then we would be able to tell what is going to be the equilibrium omega or equilibrium spin period. So this is usually displayed in a diagram of log B versus log P, and you have a line which is called the spin-up line. Stronger field neutron stars will achieve an equilibrium spin-up at a longer period. Lower field neutron stars will achieve spin-up at a shorter period. And all millisecond pulsars we know are here. So here the fields are about 10 to the power 8 Gauss. For Hull-Stellar pulsar, which is also close to this line, field is 10 to the 10 Gauss. And the regular pulsar population is at 10 to the 12 Gauss, which is further up here. This is Hull-Stellar. These are millisecond pulsars. And from this and various other observations, we know that all of these objects have actually come through this kind of evolutionary history where neutron stars have accreted matter and have acquired their spins. There's also another piece of story which I will not be able to go into these lectures, and that is how did the magnetic fields get so low? Those which are not in a binary system have a much higher magnetic field. So binary system has something to do with the reduction of the magnetic fields of neutron stars as well. But that's a story for another time. One thing I'll end by saying is that we talked about material being entrained by the magnetic field, being directed by the magnetic field, being brought to the surface. So if you now focus a little bit on the fate of matter once it reaches the surface. So let's say this is the polar cap. So there's a range of field lines which will connect to the accretion disk. So let's say those field lines end up in this region, that's the polar cap. So material is coming here and filling this. What will happen after that? Will the material go to the full surface? Will it stay over here? Because mass is continuously coming in. So the idea is, because of the magnetic stresses, this is going to be able to retain a mountain of matter over here, which is supported by the magnetic field itself. The weight of this matter is supported by the magnetic pressure gradient in the polar cap. How much matter can you retain in the mountain? There is a whole variety of estimates depending on what assumptions you make. So the highest values come from groups of Melatos. So they look at this problem in 2D and have material coming here, and then the magnetic field will distort itself. And inside that, it's like a magnetic bag which holds material. And they estimate that up to delta M in the mountain, 10 to the power minus 5 solar mass can be held. This is Melatos et al. But we have also looked at this problem from another angle, where we do not 2D but 3D calculations. We take plasma and then fill this with the magnetic mountain, and then look at plasma instabilities. So if you now look at this from the top, you have, so in this calculation, it's all a circularly symmetric, nice circularly symmetric distribution. But what we find is that as soon as you fill this with plasma and there is a strong magnetic field, the magnetic field bunches up. So you have regions of strong magnetic field, very weak magnetic field, strong magnetic field, weak magnetic field, and so on. So there are many modes of this distribution that gets created. And the pressure in these weak magnetic field zones is much, much smaller than the pressure elsewhere. So this matter which is accreting now actually flows out of these regions. And then it occupies the rest of the surface. So as you're continuously pouring material on the top, obviously the matter has to find a way to then eventually escape these confines and cover the whole surface. And this appears to be the mechanism by which it can do this. But once you take this into account, we find mountain masses which are much smaller. Million times smaller. This is, you can look at. The ellipticity of the neutron star that will be created by this mountain is roughly equal to the amount of matter in solar mass. It's a delta m divided by the mass of the neutron star, which is 1.4 solar mass. So here the epsilon could be of the 10 to the power minus 5. Epsilon is only of the order of 10 to the power minus 11. So the predicted gravitational radiation due to these mountains for this is about 10 to the power minus 26. For us, it's about 10 to the power minus 32. You will hear more about accreting mountains in the next course, I believe, because I saw it listed. But roughly speaking, this is the current result. Neither of these set of calculations are totally complete. It's very complex computation. But my gut feeling is that without including plasma instabilities, the calculations are really incomplete. The scenario is really incomplete. Because you need to have all the plasma instabilities which are inevitable in such strongly magnetic system to be accounted for. And that cannot be accounted for unless you do a full 3D calculation. I'll stop there and have questions. So if you want the neutron star, so a sustained accretion in a low mass X-ray binary, as I said, if the conditions are right, can increase the mass to large values. And you may sometimes be able to do that. If you want to have multiple episodes of that mass transfer, then once one star has finished supplying mass, you have to discard it and put a new star over there. So that's possible in globular clusters. Yeah, we are not changing the internal equation of state of the neutron star. The mass will change, and all the consequent effects of whatever changes happen when, so if the mass changes, the central density changes, right? And at a different central density, the internal composition may change somewhat. But equation of state is a family. I mean, for any value of density, you should be able to tell what is the composition, what's the pressure as a function of that density. So that family, we are saying that we are not changing that in this whole process. Yeah. Yeah. No, the mass accepted going beyond the Eddington limit. So mass transfer beyond the Eddington limit, there is no limit, because it's a different object which is trying to transfer mass. How much in the object inside can accept, the other object which is transferring mass doesn't care. The transfer rate can be anything. Can the neutron star accept matter at a rate larger than the Eddington limit that we know? In the common envelope phase, for a little while, that can actually happen. When the neutron star is in a very dense region of the core of the star, then the mass transfer onto the neutron star is at such a high rate that the temperature at the surface increases to larger than 10 to the 9 Kelvin. And once you reach that, the main cooling mechanism becomes neutrinos. And once neutrinos become the dominant factor, the neutrinos just escape. They are not pushing back on the matter that is falling. So we get into hypercritical accretion, and that can have very large rates in principle. Thank you all for listening.